Okay then, so today I'd like to first talk about subspaces and then get on to the very interesting topic of homeomorphisms, which I really think is one of the most fascinating ideas in topology. So we'll start with this idea of subspaces, which is also quite interesting and has some fairly surprising implications. So it's a very natural idea. Basically, a subspace topology is just a topology induced upon a subset of a topological space. But let's define it properly. So let X tau be a topological space. And also let Y be a non-empty subset of X. So Y is a non-empty subset of that space. Now, the topology induced on Y, we denote it as tau subscript Y, and it's defined to be just equal to the set of open sets of the original topology intersected with this set Y. So to get this induced topology or subspace topology, we just take the collection of all of the open sets of the original topology and get each of those open sets and intersect it with the set Y that we were interested in finding the topology upon. So this is called, it has many names, but it's called the subspace topology on Y. It also has other names. Sometimes it's called the relative topology. Sometimes it's called the induced topology. Sometimes it's called the topology induced on Y by tau. So it has lots of different names, but I think it's fairly clear what it is. And also a little bit more notation. So Y tau subscript Y is called the subspace, is said to be a subspace of the topological space X tau. Okay then, so I'll leave it as an exercise to you to prove that this is actually a topology always. So this is a problem for you to do. It's fairly easy, but it's important to show. Problem is to show that that tau Y is always a topology on the set Y. Okay, so now let's have a look at some examples of some subspaces. So here's a kind of simple example. Suppose that our set X is just equal to a set containing A, B, and C. And let's choose the topology. I think we've considered this before. It consists of X, the empty set, A, and BC. Now, suppose we're interested in the subset Y equals just A and B of this space. So, what's the subspace topology on Y in this case? So, in other words, what is tau Y? What's the topology induced on AB in this case. Maybe you'd like to try and figure this out for yourself. You can pause the video and have a go. So we can write it like this. Might as well do it in longhand. So we take each of the members of the original topology and just intersect them with y. Dash tool. I shall have to put that one down there. My pen always breaks in that corner of the screen. I'm not sure why. Anyway, so BC intersection Y. Okay, so we can simplify that. So x intersection Y is just going to be equal to Y, since Y is a subset. Empty set intersection Y is obviously the empty set. A intersection Y is just A, because Y is AB. And BC intersection Y is just B. So this is actually the discrete topology on AB in this case. Okay then, so another fairly interesting idea to do with subspaces is when you consider the idea of the basis of a topology. So there's another thing I'd like you to verify. So I'll say that it's a proposition, but I'll leave it to you to prove it. It's not too hard to prove. So the proposition is that if B is a basis, for a topology tau on X, then this thing which we're going to call B subscript Y, and we'll define it as the set of all intersections of elements of the original basis with the set Y. Well, that's going to be a basis for the subspace topology. Tau Y on Y subset X. So this is what I'd like you to try and prove. That basically, if you get the basis kind of, well, we'll call this, we might as well give it a name, since everything else in topology has a definition and a name. So we'll call this the basis induced upon Y. So it's basically just, you get all of the elements of your original basis of tau on X, and you just intersect each of those basis elements with the set Y. And we're claiming that this is actually a basis for the subspace topology you get on Y. So just in case you've forgotten, the definition of a basis, so a collection of a collection of open sets is a basis for a topology tau when we have that for every open set in the topology, there's going to be a set of basis elements S that's union is equal to the open set. So using this definition, I think you can pretty directly prove this proposition. Might as well call it proposition A just to keep everything named. Okay, so now we're going to have a look at some pretty interesting examples. well, we're going to move on to one in a minute. First, I'll just look at a fairly trivial one on the real numbers. So we're going to turn to the familiar Euclidean topology. So remember what a basis is on the Euclidean topology. So you should recall that the set of all open intervals is a basis on the Euclidean topology on the reals. So what we're going to do now is we're going to consider the subspace topology on the closed interval from 1 to 2. Okay, so what does that look like? Well, according to our last proposition, we can figure out what the basis. We can figure out a basis for this topology here. So all we have to do is take our basis up here, this thing, for the original Euclidean topology, and intersect every element of this basis with our subset closed interval from 1 to 2, and we'll get a basis for that closed interval. So let's do it. So what we get is that the set of all AB intersection 1, 2 such that A and B are reals and A is less than B. Well, that's going to be a basis on the subspace topology on 1, 2. But let's just rewrite it before we say that. So we can simplify this. This can be rewritten as AB, the set of all AB, such that 1 is less than or equal to A, which is less than B, which is less than or equal to 2. So it's a set of all open intervals, sets of numbers greater than A and less than B, where A is greater than or equal to 1 and B is less than or equal to 2. Okay, and what we're saying is that this is it's a basis for the subspace topology on 1, 2. That is with respect to the Euclidean topology on the real line, as usual. Okay, so we can get these kind of scenarios where we just take a subset of the real numbers and then ask what topology does the Euclidean topology induce upon that subset. And here's where we get a little surprise, because it turns out that sometimes you get rather peculiar kinds of open sets appearing in this kind of way. So when we take a closed interval, the result like this is fairly natural. Like the open sets on this closed interval are just a load of, the basis elements on this closed interval are just a load of open intervals, as we'd imagine. Well, let's look at a different scenario. So let's find a new page. Do some rubbing out. Okay then, so time for our surprise. Let's consider the subsets which is the closed interval from 1 to 2, subset of the reals. Now, a basis for the subspace topology induced on 1, 2 by the Euclidean topology on the real line is going to be equal to just the set of all intersections of open intervals with this closed interval 1, 2. That seems very logical. Now we get something fairly interesting, because let's sort of expand out this set. What is this set here? This is a set of basis. This is a set of basis elements for the subspace topology on 1, 2. Well, let's expand it out. Well, we can write it as the union of 3 different sets. So, firstly, one part of it is that it consists of a set of open intervals such that 1 is less than or equal to A, is less than B, is less than or equal to 2. So that's one part of it. But we also have, and this is where things get a bit different, we also have other kinds of basis elements. For example, 1 to B, such that 1 is less than B is less than or equal to 2. So these kind of basis elements here, these kind of things, you get those by taking an open interval, AB, and intersecting it with 1, 2 when A is less than 1. Okay, and we also have, kind of symmetrically, we also have another kind of element in this collection of basis elements, which is the set of numbers which are greater than A and less than or equal to 2, such that 1 is less than or equal to A is less than 2. Okay, so of course every element of a basis is going to be an open element of the topology. So we get the very interesting conclusion here, I think it's very interesting, that, for example, if we look at this case here, we have that 1.5, the set of all numbers which are greater than or equal to 1 and less than 3/2, is an open set. On the subspace topology on 1, 2. So when we look at subspace topologies, the open sets aren't always of the same kind as the open sets of the initial kind of topology on the superset. Okay then, so I've got another question for you before we move on to something else. So one final question. Maybe I should just recklessly delete this top line to make space for it. So here is the question. what is the subspace topology induced on the integers by the Euclidean topology on the reals? Okay, so of course you know about the Euclidean topology on the reals, and the integers are a subset of the reals. So what kind of form does the subspace topology on the integers have? And you should be able to identify it with one of the kind of famous topologies which we talked about in the first lecture. Okay, so now I want to get on to one of my favourite topics, which is homeomorphisms. But just before that, I want to make sure that people understand what I mean by a mapping. So a mapping, let's just talk about mappings in general. So suppose we've got a couple of sets, x and y. So we write a mapping from x to y. I write it like this. So f maps x to y. Sometimes it's also called a function from x to y. And what basically it means is that for every element of x, there's an element of y, which we call f of x. It's just an element of y. Okay, so diagrammatically, say this is x, just say it's a set of 3 points or something, and this is y. So we're just going to be sending each element, so say this is x, little x, this is going to get sent to a particular element of y, which we're going to call f of x. Okay then, and so, well, let's just make up a mapping, shall we? So suppose this gets sent here, and let's suppose in this case that both of these points here both get sent to this point down here. And let's give these things names as well. Why not? We'll call this one, we'll call this point 1, this point 2, and this point 3. Okay? So a little bit of notation is that, say we've got this mapping here from x to y. Now, for a member of y, we're going to define the inverse of the mapping on this element to be equal to the set of all elements of x which get sent to y by this function or mapping f. So in this example here, we're going to have the inverse of the point. Okay, so let's give these names as well. We'll call these ones A, B, and C. I know that's called X as well, but it doesn't matter. So f to the minus 1, or the inverse of 0.1 in y, is equal to the set AB, because both points A and B in x get sent to 0.1 in y by the mapping f. Also, the inverse of 0.2 in y is equal to the empty set, because nothing gets mapped to 0.2 in y. Okay, and just to extend this idea, Suppose we now have a subset A of y, then we'll define the idea of the inverse of the mapping on the subset to be equal to the union of the inverse of all the points of that subset. Okay, so for our example down here, we'd have that the inverse on the set, let's say 1, 2, well, that's going to just be equal to the inverse of the point 1 in union with the inverse of the point 2. And this is going to be equal to just AB again. So more kind of verbally, you'd say that the inverse of a set of points in Y is the set of all points in X which get mapped. Sorry, you'd say that the inverse of a set A of points in Y is the set of all points in X which get mapped to points in A by this mapping F which sends X to Y. Okay, so that's a little bit about mappings. I guess since we're talking about mappings, I might as well just mention a couple of other things which you might well have seen before. No, actually, I think I'll leave it. I'll talk about them inside the definition of a homeomorphism. So let's get on to that nice idea. Okay, so here we go. Let x tau and y tau 1 be topological spaces. Now, we're not supposing any relationship between these two. We're not supposing that y is a subset of x or anything like that. These are just two independent topological spaces. Now, these two spaces are said to be homeomorphic when there exists a mapping or function f from the set x to the set y, which is such that we have a few conditions holding. Okay, so firstly, we have that f is a one-to-one mapping. Now, I know many of you might know what that means, but I'm going to I'll talk about what it means in a second anyway. But the second condition required is that f is an onto mapping. Okay, so basically one-to-one means that every point in x gets mapped to a distinct point in y. We don't have 2 points in x getting mapped to the same point in y. F is onto means that every point in y gets mapped to by some point in x. Condition 3 is that we have that for every open set, of the topology on Y, which is tau 1, we have that the inverse of the mapping is actually going to be an open set of the topology tau on X. And finally, condition 4 is rather similar. It says that for every for every open set V within our initial topology on X, we have that the image of that set V is a member of the topology tau 1 on Y. Here I don't think I mentioned, although it's probably evident by this point, that if we have a subset A of a set X, and we have this mapping F from X to Y, then what we mean by F of A is equal to the union over points X of A of F of X. Okay, now let me just verify what these terms one-to-one and onto mean. So the mapping is one-to-one. What that means is that if we have a couple of points in X, X1 and X2, then F of X1 equals F of X2 implies that X1 equals X2. So we never have this case where two different points in our set capital X get mapped to the same point in capital Y. And also this onto condition, what that means is that for every point Y in the set Y, there exists a point little x in the set capital X that gets mapped to that point Y. Okay then, so that's our definition of when two spaces are homeomorphic. And when these conditions hold, when we've got all of this stuff, then we say that F is a homeomorphism between the topological space X tau and the topological space Y tau 1. And sometimes we write it in shorthand, so we write it like this, that X tau is similar. So it's kind of like an equal sign, but we have a curly bottom line. Well, that's how I write it anyway. Y tau 1. Okay, some people use slightly different notation to this. Okay, so the fact that I'm using something like an equal sign should give you an idea about what homeomorphism means. Basically, a homeomorphism is the important equivalence operation in topology. And essentially, when two spaces are homeomorphic, they are pretty much the same as far as topologists are concerned. So just like in geometry, if you can transform two figures by rigid motions, you can transform one into the other, then they're considered the same in geometry. Well, in topology, if you can transform one topological space into another via a homeomorphism, then they are considered the same. And so this is actually an extremely powerful concept, because what it allows you to do in actual practice is to take something really complicated and do a homeomorphism on it, or prove that it's homeomorphic to some idealized simplistic example which you understand the topology of very well. And this is done a lot, and so it's going to be very important for us to understand about homeomorphisms. Okay, so later on we're going to see a different way to formulate the idea of homeomorphism. So basically a homeomorphism is a one-to-one mapping from a set onto another set, which is continuous and has a continuous inverse. Those are the meanings of statements 3 and 4 in what we've just looked at, although I'm not going to officially talk about continuity for a lecture or so, I'm not going to go into the details of what I mean by that. Essentially, I mean that it preserves limit points, but we'll talk about that later. The important thing, though, is, like I say, the idea of homeomorphism is the central gives us the central idea of equivalence in topology. So in fact, when two topological spaces are homeomorphic, so say we've got a topological space X tau and Y tau 1, then if they're homeomorphic, I write it like this with a kind of wiggly equal sign. And in fact, we have the this wiggly equal sign is an equivalence relation. So this is something which is defined in its own right, but essentially all it just means is that this thing here satisfies 3 different conditions. Namely, it satisfies the conditions that it's what you call reflexive, which basically just means that any element is every topological space is homeomorphic to itself. The second condition is that it's symmetric, which just means that if a topological space A is well, I'll just write it down. So if X tau is homeomorphic to Y tau 1, then that implies that Y tau 1 is homeomorphic to X tau. Now, I'd like you to try and prove this second point for yourself. So then the third point, which is very important, is that this homeomorphism is a transitive thing. And what that means is just that if we have 3 topological spaces, so we have that if our topological space X tau is homeomorphic to another topological space Y tau 1, and also we have that Y of tau 1 is homeomorphic to another topological space, let's call it Z tau 2, then together all this stuff implies that X tau is itself going to be homeomorphic to Z tau 2. Okay, so if we have conditions 1, 2 and 3 holding, then we're going to have that a homeomorphism is indeed an equivalence relation, and it is. And basically we're going to prove it together. So I'd like you to show points 1 and 2, and I'll prove that point 3 holds. Okay then, so we're going to try and prove that point 3 holds now. So we're going to have that there exists homeomorphisms F. There exists a homeomorphism F, which sends the topological space x tau to the topological space y tau 1. And also we're going to have that there exists a mapping G from y to z, which basically is a homeomorphism from the topological space y tau 1 to the topological space z tau 2. Okay, so given all this, how are we going to prove point 3? Well, what we want to do is construct a homeomorphism from x tau to z tau 1. And for this, I propose the composite map. So the composite map, which we write as G circle F. And this is a mapping from x to z. Whoops. Mapping from x to z, in fact. So we want to show that this mapping, which we get from composing G and F, is a homeomorphism from the topological space x tau to the topological space z tau 2. So how are we going to do it? Well, first let's look at what this notation here actually means. What it basically means is first apply the mapping F and then apply the mapping G. So in particular, for all x belonging to the set capital X, we have that when we apply this composite mapping on x, we just get G of F of x. So first we apply the mapping G, then we apply the mapping F. Okay, so I'll leave it as an exercise for you to prove that this is a one-to-one mapping, and that it's an onto mapping. So that shows that this mapping satisfies conditions 1 and 2 required for it to be a homeomorphism. Now we want to show that it satisfies proposition 3. So I say proposition 3, I mean parts 1 and 2 of the definitions of a homeomorphism. Now we want to show that it satisfies part 3 of the definition of a homeomorphism. Okay, so we want to show that this composite map satisfies property 3. So what is property 3? Well, what property 3 says is that essentially the inverse of every open set, which is in, well, in this case in tau 2, is an open set in our original set tau. Okay, so to begin our proof of this, we're just going to suppose that U is going to be any open set in the topology tau 2 on the set Z. Okay, so we have that G is a homeomorphism. So let's write it down. Since G is a homeomorphism, do I have space to put a diagram somewhere? Maybe I can write a little diagram up here. Just to remind, so we have x tau, and then a homeomorphism F sending it to y tau 1, and another homeomorphism G sending that to Z tau 2. Okay, so since G is a homeomorphism, then G itself is going to satisfy property 3, and so since G is a homeomorphism, we're going to have the inverse of U is going to be a member of the topology tau 1. And then since F is a topology, since F is a homeomorphism, I won't bother writing it, but since F is a homeomorphism, by similar logic, we're going to have that f to the minus 1 of G to the minus 1 of U is going to be a member of the topology, the original topology tau. And in fact, what f to the minus 1, G to the minus 1 is it is actually exactly equal to, so this is actually equal to the inverse of the composite map. So as my old school teacher used to say, if you think of F as putting your socks on, and then G as putting your shoes on, then the inverse of that would be first taking your shoes off, and then second taking your socks off. Okay, so this is just equal to the inverse, and so what we've basically shown now is that the inverse of our composite map takes an open set in our topological space on Z, and it changes it back to an open set on our topological space on X. So we've shown now that this composite map satisfies condition 3 of the required homeomorphism things. So now we've got conditions 1, 2, and 3. We just need to show that we've got condition 4. So that's actually even easier. Okay, so condition 4 let V be a open set in the topology tau. Now since F is a homeomorphism, F of V is going to be a open set in tau 1, and since G is a homeomorphism, G of F of V is going to be an open set in tau 2, and G of F of V is just equal to the composition of G and F acting on V. So this now shows that we have condition 4. So we've already shown condition 3. This here shows we have condition 4 as well. So this composite map here satisfies conditions 1, 2, 3, and 4 required for our homeomorphism. So it is a homeomorphism. So X tau and Z tau 2 are homeomorphic. QED. The reason I think that homeomorphism is such a neat concept is because if two topological spaces are homeomorphic, then, as I've already said, the topologist pretty much thinks of them as the same. So we think of them as pretty much the same because they have the same topological properties. And so whatever properties get preserved by homeomorphisms, we're interested in, and whatever does not get preserved, we're not interested in. And so now what we're going to do is we're going to see that length is not a topological property because it's not preserved by homeomorphism. So in particular, I want to just give an outline of a proof that if we have any open intervals, so let me write this here. So we've got any pair of open intervals, A, B, and C, D, then they're actually going to be homeomorphic to each other. So in other words, the set of all numbers between 0 and 1 is homeomorphic to the set of all numbers between 7 and 50 trillion. Length is just not a topological property. So really thinking about homeomorphism allows one to solidify this concept of why topology can be thought of as rubber sheet geometry, as it's often referred to. But anyway, let's talk about something more concrete. Let's try and prove this result, or at least sketch why it's true. So, because homeomorphism is an equivalence relation, it suffices to show that every open interval is homeomorphic to the unit open interval. And once we've done that, we can easily go backwards and forwards. So essentially, if we show a generic open interval is equivalent to the open interval, then we can transform, we could go from, if we want to transform this, we can go from here to the open interval, and then we can do another homeomorphism to get here. Because if we know that both of these are homeomorphic to this, then it follows from the transitivity and reflexivity of the homeomorphism relation. So, okay, basically what we want to do is show that any open interval is homeomorphic to the unit open interval. So let's write this down properly. So for all A and B in the reals, such that A is less than B, what we want to do is show that this open interval here is homeomorphic to the open interval from 0 to 1. So actually, we're going to do it the other way around. We're going to find a homeomorphism F, which sends the open unit interval to the open interval between A and B. So here we go. Let me start with a diagram. Now let me start by telling you what the homeomorphism is. The homeomorphism is just a mapping like this, and it's defined such that for every element in the open unit interval, we have that f of x is equal to 1 minus x, 1 minus x times a. I'll write it a bit neater. Plus b times x. Okay, so this is our supposed homeomorphism. And so let's just look at a diagram, because it's much clearer to see on a diagram. So here's our x-axis, where little x lives. And here's 0, and here's 1, and here's a, and here's b. And so this is actually a graph of our function, or a plot of our function. And so what we're doing here is for any particular point within the unit interval, let's say this one here, we're mapping it. So this is a point on the horizontal unit line. We're mapping it to this point here on the vertical line between A and B. So hopefully you can see, although I'll try and, well, okay, so let's try and argue this a little bit more rigorously then. So you should be able to see that this mapping is a one-to-one onto mapping. You should be able to see that even from a diagram. Now, also, it should be clear from this diagram that this mapping is going to be sending open intervals between 0 and 1 to open intervals between A and B. So, in particular, let's say we've got some open interval here. Well, that's going to get mapped to. Oh, it seems to have disappeared. An open interval here. So let's say that B lives up there. A lives down there. Okay, so hopefully you can see that open intervals between 0 and 1 are getting mapped to open intervals between A and B, and also conversely. So basically what we're trying to say, I'll write it a little bit more notationally. So we're saying that the function of an open interval is going to, of an open interval in the unit open interval is going to be an open interval between A and B, and also hopefully you can see conversely that by a similar kind of thing. So this also implies that open sets get mapped to open sets, and conversely hopefully you can see that the inverse of this function, so the inverse of this function, well, let's define it with respect to y. So just by manipulating this function here, we can find what its inverse is, and that's another linear function. It's just equal to y minus a divided by b take away a. And hopefully you can see that really by a similar kind of argument, this also maps open sets to open sets. And so this mapping F satisfies our conditions 1, 2, 3, and 4 of a homeomorphism, and so F is a homeomorphism. I know I haven't shown this rigorously, but you can fill in the details for yourself. Okay then, so now let's prove something that's even more interesting. So what we're going to show now, we've just shown that any pair of open intervals are homeomorphic to each other. Now we're going to show that any open interval is actually homeomorphic to the entire set of real numbers. This is quite amazing, really, I think. You know, the whole set of real numbers is basically topologically just the same as the numbers between 0.1 and 0.12 or something. So to do this, what we're going to do is we're going to show that, or we're going to argue, actually I'll just give a sketch. So we're going to show that the interval of numbers between -1 and 1 is homeomorphic to the set of all real numbers. And basically our homeomorphism f of x is just x divided by 1 plus the absolute value of x. Absolute value of x, you probably already know, but I do like to make sure everything's clear. So absolute value of x is it's equal to x. Okay, so it's equal to x when x is positive, and it's equal to minus x when x is negative. So absolute value of -7 is 7, and so forth. Okay, so, well, if you look at this mapping, I'll leave the details to you, but let me just draw a plot so that you can see basically what's going on. So here's -1, and here's 1. And if you do a plot of this mapping, f of x here, so this is x, and this is f of x, then what you'll see is that the plot looks something like this. It has asymptotes at -1 and 1. Well, I'll draw it in blue, it's prettier. And it goes kind of like this. And you can show that, you know, for any number y, you can find an x that maps to y. And you can show that this is invertible, and it's an increasing function, so it's going to be 1 to 1 and on to, and you can show that it sends open sets to open sets, and its inverse does similar. So this is a homeomorphism from this open interval to the whole set of reals, and of course, as we've just shown, any pair of open intervals are homeomorphic, so any open interval is homeomorphic to the entire set of reals. So topologically, they're the same. It's interesting that these really different looking objects are really very, very similar, from our perspective at least. Another result, which you might have guessed by now, is that any two closed intervals are homeomorphic. Okay then, so now we're going to look at another very interesting example, and this is going to shed light on a lot of things. The idea of homeomorphisms, subspaces, and connectedness. So firstly, let's consider the subspace of the Euclidean topology on the reals that's just induced upon this funny subset of the reals between 0 and 1 in union with the reals between 2 and 3 inclusive. So if we just visualize this on the real line, so here's 0, 1, and 2, and 3, and 4. It looks like this, okay? So we would usually say this is disconnected. So is it disconnected in a topological sense? Well, yes, it is. So let me give you a quick proof of that. Maybe you'd like to pause the video and show that this is a subspace here, induced on this topology, is disconnected. But let me have a, so I'll have a go. Let's see now. Minus a half, three over 2 is an open set on the Euclidean topology in the entire line. And so the open sets on the subspace topology on here are going to be the intersections of the open sets of the Euclidean topology on here with this set. Okay, so then this implies that okay, so let me just give this a name. I'll call it S. So it implies that -1/2 to 1.5 intersection S will be open on the subspace topology on S. Okay, but what is this? Well, what this actually equals, maybe I'll write it in red, it's just equal to the set of all numbers greater than or equal to 0 and less than or equal to 1. Okay, so that's actually an open set in this topology, in this subspace topology, and by exactly the same, well, by exactly analogous reasoning, 2, 3 is open on the subspace topology on S. And so now consider this subspace topology. So let's use blue now, a bit of multicolours. So we've got S, and then we've got tau S. That's the collection of all open sets in the subspace topology on S. So we have that we've just shown that 0, 1 is a member of tau S. It's an open set in this topology. And so is 2, 3. Now, the complement of 0, 1 in this space, so S take away 0, 1 is actually equal to 2, 3. So that is the complement of an open set. So that must be closed, in fact, on this subspace. So we also have that 2, 3 is closed on the subspace topology on S. So it's clopen. So in fact 2, 3 is clopen and 0, 1 is clopen, and so by the definition of a connected topological space, this space is not connected. It's disconnected, as it should be. It agrees with our intuition. Okay then, so you might be wondering what this discussion about connectivity in subspaces has to do with homeomorphisms. Well, I'll tell you. Basically, so far we've been talking about when spaces are homeomorphic. Now, another problem, which is often a bit more difficult, is to show when two spaces are not homeomorphic. Okay, so how do you show a couple of spaces are not homeomorphic? Well, I want to give you a couple of examples. I want to give you an example of a couple of spaces which are not homeomorphic, then show you a proof. So we've got the Euclidean topology. And we have that the subspace, which we've just been talking about, the numbers between 0 and 1 and the numbers between 2 and 3, is not homeomorphic. Maybe I'll write it like that. It's not homeomorphic to the closed interval of numbers between 0 and 2. Why not? Well, basically the intuition is that this set here is disconnected or not connected, and this set here is connected. And connectivity is a property which is preserved by homeomorphisms. It's a topological property, and so since these are not, they don't both have the same state of connectedness, they can't be homeomorphic. But let's give a better proof than that, because it's quite illustrative. So we'll call this space here, let's call it y tau 1. So this is this set with the Euclidean topology, subspace topology induced on it, and similarly we'll call this space x tau. Okay. Now what we want to do is we want to prove that x tau does not not equal. Of course, it's not equal, but we want to show it's not homeomorphic to y tau 1. So we'll do a proof by contradiction. So suppose that they are homeomorphic, and then suppose that f is a homeomorphism from x tau to y tau 1. Now f, the inverse of f operating on the open interval over here. So we've got an open interval from this set space here, and we'll do the inverse operation on that, and that should be a Clopen set, a Clopen subset of x. Why? Well, because it's Clopen in y. In other words, it is open and its complement is open, and so you can show that by the properties of homeomorphism, that should be preserved by the inverse of this f operation. So the inverse of the closed interval should be a Clopen set of x, but that cannot be, because x is equal to 0, 2, and it's connected. It's a connected space. So it can't have a Clopen set which is not equal to the empty set or the space itself. But we just said that it did. So that's a contradiction. So we assumed these spaces were homeomorphic, and we got a contradiction. That's the basic idea. So what do we learn from this? The main thing we learn is that, might as well call it a proposition. No, I'll just write it as a statement. So if a topological space not enough space to write there. Let's put it here. Recklessly destroy that writing and just a little box here. So any topological space homeomorphic to a topological space to a connected topological space, is itself connected. Essentially, basically, connectivity is preserved by homeomorphisms. And we'll see many other properties that are preserved by homeomorphisms, and they're precisely the topological properties. They're the interesting things which don't get changed by these continuous deformations, essentially. Okay, thank you for your attention.